All right, next we are looking at the integral of x to the fifth times e to the x cubed dx. So I see a power here times an exponential, so I am thinking integration by parts. So how about let's pick our u and our dv. So usually, you want to pick u so it's got a simpler derivative here. So x to the fifth would be maybe my first choice there, and then dv e to the x cubed dx. And so if you differentiate this, it'll definitely be simpler getting to your du here. But your v, when you want to go from dv to v, you're doing an antiderivative there. How do I do the antiderivative of e to the x cubed? That's e to a function. Antiderivative of e to the x is e to the x. I know how to do that. This, I don't know how to do. That's kind of got me puzzled. Okay, so, well, what if we switch them? If I put the x to the fifth over here, put the x to the fifth there, I can definitely do an antiderivative. I get x to the 6 over 6. But then my u to du, if I differentiate that, I would get e to the x cubed. And since it's e to the function times derivative of the inside function times 3x squared. Well, that's not a simpler derivative. That's more complicated. That's going to appear in the new integral. I don't want more powers in there than what I had before. So this one, either direction, you've got problems here, So what are we going to do with this? Well, it turns out here that we need to use a u substitution to simplify this first before we do our integration by parts. And what I see here is if I take this x to the fifth, and you wouldn't see this unless you've seen an example probably, but take that x to the fifth and break it up as x cubed times x squared. And then we've got that e to the x cubed and dx. And now I look at this and I see a function x cubed here, and its derivative is 3x squared, and there's the x squared. So maybe I need the 3, so I'll multiply by 3 and compensate outside with a 1/3. And now I do see a function and its derivative. Here's the 3x squared dx. That's my derivative, and then x cubed is the function. Okay, so why don't we do a substitution here? I'm going to use a different variable instead of u. I'm going to do u substitution, but let's let w be our variable. So w equals x cubed. And then dw is 3x squared dx. So now let's change this into the new variable. So we got that 1/3 out in front. This will be integral. The 3x squared dx, that is my dw. And then I've got an x cubed there and e to the x cubed there. So that's going to be w e to the w. So that simplified it. So now I do have still a power times an exponential, but now I know how to integrate the e to the w. So now we'll go ahead and do our integration by parts in the next step. So u, I'm going to let that be w, and then my dv is going to be the e to the w dw. So this is my dv, and that's my u. So here I've got e to the w, and then instead of dx, it's dw because we did a simplifying u substitution first. And now our derivative here, derivative of w is just 1 and dw. And then from dv to v, we're doing an antiderivative. Antiderivative of e to the w is just e to the w. So that was an easy antiderivative. So now we can go ahead and change this over. So now we're going to have uv minus integral of v du. So our uv is our diagonal product, w e to the w, and minus integral v du is our product on the bottom line here, so e to the w and dw. Okay, and that's definitely an easier integral than what we had up here. And then we also have that 1/3 out in front right here. So we need to do 1/3 around this whole integral, or whole expression. And now I can go ahead and multiply the 1/3 in here times each piece. So I've got a 1/3 w e to the w, and then minus 1/3. And now we'll go ahead and do our antiderivative of e to the w is just e to the w, and then plus constant. And now we just have to reverse our w substitution, put back in the x cubed. So this will be 1/3 x cubed e to the x cubed minus 1/3 e to the x cubed, and then plus constant. And we got it. So that was a two-step. U substitution followed by an integration by parts. And sometimes you have to do that.